Okay, so here we have a setup of a brick hanging from a string which is attached to a spring scale alongside my lovely assistant Nick Crowder. And so we see here that the brick is in equilibrium. How do we know it's in equilibrium, Nick?
Because it is not moving.
It's not moving, and an object that's not moving or moving at a constant velocity is in equilibrium. So, Nick, can you tell me a force that should be acting on this brick?
Gravity.
Going which way?
Down.
Down. Good. So we have gravity or weight going down, and any other forces, Nick?
No.
No other forces are acting on this brick.
Is it a natural force going up?
There is not a natural force going up. We have a force exerted by a string. What do we call that force, Nick?
Tension.
Tension going up. Good. So what do we know about the tension going up and weight going down, Nick?
They're equal.
All right. All right, so what we talked about there is we have that brick suspended by a string, which is attached to a spring scale, and there are two forces acting on that brick, and the first one is weight, and weight is the force of gravity acting on an object near the surface of a planet. And the way that we can always calculate weight is that weight equals mg, where m stands for the mass in kilograms, and g is the acceleration due to gravity, and on Earth g is 9.8 meters per second squared, or 10 meters per second squared. Alright, and the other force we had acting on the brick was tension. And tension, let's see if I can, is a force exerted by a string or rope on an object. Okay? So we have weight acting on our brick, which is a field force, and we also have tension acting on our brick, which is a contact force. And the question was, if we have a 1.5 kilogram brick, what is the tension in that string? So let's look at how we can solve that. Alright guys, so whenever we're solving an equilibrium problem, the first step is always going to be to draw a free body diagram. And the first thing we do in a free body diagram is we draw a box, and that box represents our object. No matter what the object is, we usually just draw a box to represent it. And then from that box we draw vectors or arrows representing the forces. So as we said earlier, we have weight acting on that brick, and the symbol I use for weight is just mg, because that's how we end up calculating weight. We do the mass times the acceleration due to gravity. And then, as we said, the other force acting on the brick was the tension that was pulling up on the brick, the tension in the string. And then the one thing we know is that m equals 1.5 kilograms, and of course we always know g is 9.8 or 10 meters per second squared. Step 2 for solving these problems, we're actually just going to leave blank for now because we're not going to get into that until Thursday. So for right now, don't worry about it, but just realize there is a step 2. And then step 3 is going to be to write your system of equations for equilibrium. Alright, so in this case we know that net force in the x direction has to equal 0 because we're in equilibrium. We know we're in equilibrium because we're not moving. And there are no horizontal forces, so I don't have anything I really have to write there. And then we also know that net force in the y direction has to equal 0 because we're in equilibrium, we're not moving. And we do have vertical forces, so what we know is that the force up minus the force down has to equal 0. Another way of saying that is that the force up has to equal the force down. So if we want to solve for the tension in that string, then we need to take our mass and multiply by our acceleration due to gravity. And if we do that, we're going to find that our tension is about 15 newtons. So now what we're going to do is check. We've asked Nick to measure the tension on that spring scale, and we're going to see how we did, see if our theoretical value comes out to the actual value he measured. All right, Nick, so we've solved for the tension, so why don't you read it off the spring scale there and we can see if we got it right.
The tension is 15 newtons.
All right, thank you very much, Nick. All right, so what we see there is physics worked. We predicted a tension of 15 newtons, and that's exactly what Nick measured.